All right, so today we're gonna go over some false proofs. And a false proof is something in which you use a series of algebraic manipulations and you end up with a result like 1 equals 2. And yes, although this seems a little silly, we are going to use this to demonstrate a series of incorrect math manipulations that you cannot use when doing algebra. And also they seem pretty cool and you can confuse your friends by convincing them that 1 equals 2. And without further ado, allow me to share my screen. Okay, so do you all see this?
Yes.
All right, so the first one is very simple. It's a demonstration of a very simple concept, but let me go over the proof real quick. So we start with 1 equals 1, right? And we know that if we subtract 1 from both sides, the two sides of the equation remain equal. So therefore, we subtract 1 from both sides. Actually, let me get my okay, it's fine. All right, so in the third line, we use the difference of squares to factor the right-hand side into 1 plus 1 times 1 minus 1. Do all of you know the difference of squares factorization, or should I go over it real quick? Joyce, Lloyd, Wen, do you guys know this factorization?
Please help me. I don't know how to do this.
Okay, so that's fine. So basically, when you have an equation like, okay, this is a minus b times a plus b. And if you use the distributive property, you would get a squared minus b squared. And one way to see this is basically to just straightforwardly apply the distributive property. So for example, you would write this a times a plus b minus b times a plus b. And then if you expand this, you would get a squared plus ab minus b times a minus b squared. Therefore, the ab's cancel and you end up with a squared minus b squared. So therefore, when we see 1 squared minus 1 squared, we can use this factorization to put it as 1 plus 1 times 1 minus 1. Does that make sense? The factorization?
Yes.
All right, great. So anyways, you use the factorization and you put the right-hand side as 1 plus 1 times 1 minus 1. And then since both sides have a 1 minus 1, you cancel them by dividing by it. And you end up with 1 equals 2. Does anyone want to tell me why we got this amazingly inaccurate result? Joyce, Lloyd, when you guys want to take a guess at what we did?
Is it because when you factor the squares, maybe it doesn't work on the number 1?
Well, when that's a great idea, like yes, indeed, in many cases, a factorization wouldn't work with the special number 1, but in this case, it's not quite, but it does have something to do with 1. I'm going to point you guys to this line right here. It has to do with dividing.
You can't just divide 0?
That's great. Exactly, you got it. So if you notice, when we divide by 1 minus 1, we're really dividing by 0, aren't we? And if you learned about like basic division, you will know that dividing by 0 does not make sense. Because, for example, when we say divide, when you do 4 divided by 2, you can think of it as you have 4 cookies and you split it into 2 people, right? Like you give each person 2 cookies. But there is no way of dividing 4 by 0, because how would you split 4 cookies and give it to 0 people, right? It doesn't make any sense. So when you divide by 0, it is an invalid algebraic manipulation. And thus it gives you these crazy results like 1 equals 2. So the moral of this proof is that you cannot divide by 0. All right, so this is a fairly simple false proof. Is there any questions? If not, we're going to move on to the next one. All right, great. So, David, you want to go over this one?
Sure. So, wait. So, we start with two variables, a and b. We let a equals to b. So a squared is essentially a times a, right? A squared is a times itself. But from this line, we know that a equals to b. So a times a also equals to a times b. So far, so good, right? We go on to the next line, and we subtract b squared from both sides. This is there's no problem with this, right? Because if you subtract the same thing from both sides, then it's good, right? And then you split a squared minus b squared using the factor theorem, and you get a plus b times a minus b. These two things are
Difference
equivalent.
of squares factorization that we just went over. For it was the 1 squared minus 1 squared. It's the same thing here, except with variables.
Yep. And then for this one, you just factor out a b. So a divided by b equals to a, and then b squared divided by b equals to b. And then after this, you divide both sides by a minus b. And then you get a b and a plus b. And since b a also equals to b, you get a plus b equals to 2b, right? So you get 2b equals to b, and you divide both sides by the variable b, and you get 2 equals to 1. Do you guys can you guys see what's the little trick we did here to create a fallacy?
Wait, actually, before we move on to that, does anyone have any questions about any of the algebraic manipulations we did? For example, do you guys have questions about how we got b times a minus b or anything about other than that? Like any questions about algebraic manipulations? All right, so I'm assuming that's clear. All right, then David.
All right, can you guys see what happened here?
Why did we get such an amazing result once again?
When Joyce, Loy, you want to give it a try? Something that's very similar to the last example happened here as well, and it gave us this fallacy.
When do you want to tell us why we got this result?
Well, in fourth line, a plus b times a minus b, that equals 0, right? And on the right hand side, ba minus b, that's also 0. And then I don't think you can distribute 0. Let me see.
When you are very close, you're on the right track. It does indeed have to be with 0, but it's not quite about distributing 0. It's about doing something else with 0.
What do we do from the fourth line to the fifth line? Can you see?
Yeah, you can't subtract 0.
Well, when you are very, very close, we are
It's not
indeed
subtracting.
doing something with 0, but it's not quite subtracting. Remember, these are multiplications, right? So
Yeah, you can multiply by 0. Well, you can, but both sides are 0.
well, when I'm gonna tell you exactly what's going wrong, you're very close, but it's not quite multiplying by 0. That's the problem, because if you multiply 0, that would be valid, like both sides would be equal to 0. What really went wrong here is that we divided by 0, right? Because since a is equal to b, if you do a minus b, wouldn't that give you 0, right? So in order to cancel the a minus b and the a minus b, we divided both sides by a minus b. And again, that's 0. And we can't divide by 0. That's how we got a plus b equals b, and therefore we got 2 equals 1.
I see.
Yeah, that's good. Lloyd, Joyce, do you guys have any questions about this?
No.
All right, great. Then let's move on to the next one. So the next one takes a turn from what we were talking about, and this is about a different algebraic manipulation that you are not allowed to do. So in this proof, we start with 9 minus 24 equals 25 minus 40. And just in case it's a little bit confusing, both sides are equal to negative 15, right? It's just two ways of expressing the difference. 9 minus 24 is negative 15. 25 minus 40 is also negative 15. And then since these two are equal, adding 16 to both sides gives us another valid equation, right? Because if you do the same thing to both sides of an equation, the equation remains true. Then this is something a little bit complicated, and I'm gonna go over it really quick. So what this is called is that when you have a minus b squared, it becomes a squared minus 2ab plus b squared. And you can derive this factorization by using distributive property, just like the way that we discovered the difference of squares factorization. So we can see this by starting with a minus b squared, which is equal to a minus b times a minus b, right? Because the number squared is equal to the number times that number itself. Using the distributive property, you would get a times a minus b minus b times a minus b. And then when you distribute that, you get minus ab minus ab plus b squared, which then gives you a squared minus 2ab plus b squared. And so now if you look at, okay, let me erase this extra stuff real quick. By the way, did that make sense? Like, does it make sense why this factorization works? All right. So using this factorization, note that how 9 minus 24 plus 16 is really 3 squared minus 2 times 3 times 4 plus 4 squared, right? Because 3 squared is 3 times 3, which is 9, and 2 times 3 times 4 is 24, so that's the minus 24, and 16 is equal to 4 times 4. So this expression right here is really, it can be written as this. And when we write it like that, we can apply this formula right here. And so we will get 3 minus 4 squared, because in this case, a is equal to 3 and b is equal to 4. So we just plug these numbers into the factorization, and we get the left hand of this. Does that make sense? How we got 3 minus 4 squared? Joyce, Lloyd, when does that make sense to you? Are there any questions?
No questions.
All right, sounds good. And the right-hand side is actually very similar to the left-hand side, because notice how this expression can be written as 5 squared minus 2 times 5 times 4 plus 4 squared. So when you use the factorization, you get 5 minus 4 squared. And then after all of this, we take the square root of both sides, ending up with 3 minus 4 and 5 minus 4, which would mean that 3 equals 5. Huh. What did we do wrong in this case? Y'all want to take a guess? Yeah, you go ahead.
I just want to ask, is it like how do you do it, or like it's something like something?
We're basically like trying to figure out why this happened. Like, what went wrong that caused us to deduce something that's incorrect from a correct statement, right? Because we started with negative 15 equals negative 15. So how did we end up with something that's not correct? Something that's like 3 equals 5. Like, how did that happen? Why did that happen?
3 equals 5.
Because I'm pretty sure 3 isn't equal to 5, right? So what happened?
Equal to 3. Totally, it's not right.
I agree, but what we're trying to figure out here is what exactly went wrong that caused this to happen. When Joyce, Floyd, do you guys want to take a guess? Any wild guess will be okay. It's a pretty subtle mistake. Take a wild guess, guys. Yeah, Lloyd, go ahead. Lloyd, we can't really hear you. All right, that's fine. We seem a little stumped. Well, I am going to review that the mistake lies in the third line. Well, to be specific, the transition between the third and the fourth line. That's right, Lloyd. The mistake lies in here. More specifically, the mistake lies in taking the square root of this, right? Because if you think about it, how did we get from the third line to the fourth line? We took the square root of both sides, right? We took the square root of 3 minus 4 squared, and that gave us 3 minus 4. We took the square root of 5 minus 4 squared, and that gave us 5 minus 4. Yeah, you want to say something?
I think I know why 3 equal to 5, because 3 minus 4 equal to 1, and 5 minus 4 equal to 1. That means 3 equal to 5.
Well, that's a great idea. However, there's the subtle mistake that you kind of made here is that 3 minus 4 is actually negative 1, right? That's kind of why things
Yeah.
went wrong, because sorry, the right hand side is actually equal to 1, but negative 1 isn't equal to 1. So when you add 4 to both sides, you get 3 equals 5, this disastrous statement that can change the entirety of mathematics. Well, guys, since we seem a little stumped, the reason that taking the square root went wrong is that when you take the square root of x squared, it is important to note that the result is not simply x, right? Because in general, when you take the square root of x squared, the number is equal to the absolute value of x. And I'm not sure if you guys learned about absolute value, but basically absolute value is the distance of a number from 0 on the number line. And to give you guys a few quick examples, the absolute value of -3 is 3. The absolute value of 4 is 4. The absolute value of -99 is 99. So it's basically like a positive number stays the same, but a negative number becomes positive. Does that make sense? Absolute value. It's a quick concept. Okay, yeah, you got it. That's good. That's good. All right, but anyways, in general, the square root of x squared is not equal to x. It's equal to the absolute value of x. Because when we define the square root function, this little symbol right here, what we're really saying is it gives the number, it gives the positive number that squares to x squared, right? For example, when we try to find the square root of 9, this function, square root as a function, it gives you 3. Even though -3 squared also gives you 9, the square root function always gives you the positive square root, right? So for another example, say that we're trying to find the square root of 16. In that case, the answer is 4. And you would say, hey, but -4 squared is also equal to 16. So how come the answer has to be 4? Well, again, the square root symbol is defined as a function, and that function only gives you the positive, or some people call it the principal root, which is why it always gives you the positive root. By the way, does that make sense before we keep going? The concept of like principal roots. It's a little confusing, it might be. Joyce, Lloyd, when does it make sense?
Yes.
Okay, good, good. And then keeping this in mind, we're gonna go back to why the square root equals the absolute value. So let's take an example. Say that we let x equal -4, right? Then x squared would equal what? 16, right? Everyone agrees. Then when you take the square root of x squared, you're really taking the square root of 16. And remember how we define the square root as a function. So someone tell me what this number has to be. Lloyd, you want to give it a try? What is the square root of 16? Notice the D, the definite article. Lloyd, feel free to type in the chat if you want to. Oh, that works too. Right, it's 4. Because again, when you take the square root of a number, it always gives you the positive root. So right, Lloyd, very good, outstanding. The answer is 4. Now, notice how while we started with -4, we actually got +4, right? Because again, when you take the absolute value of x, when you take the square root of x squared, you get the absolute value. Because this guarantees that you always get the positive root. Okay, does all of this make sense? Like, does this box statement make sense to you, all of you? Is there any questions about any of this? Because if not, we'll be moving on to the next proof, and it also involves this concept. You have a question? I see your message.
I just have a question that how can be x equal to, I mean, like, how can x equal to 16?
It actually doesn't equal to 16, right? Because in this little example of ours, x equals -4, right? Like, we define x to be -4. Let me use a different color, it's fancy. We define x to equal -4, right? So what x squared is, it's really equal to x multiplied. I'm gonna use a small x to represent the multiplication symbol. So -4 squared, what is that? That's really -4 times -4, right? So it's -4. Okay, this is kind of messy. Let me write it. I'll write it down here. So it's really equal to -4 squared is equal to -4 times -4, right? And yeah, what is 4 times 4?
4 times 4 is, let me see.
Lloyd gave you the answer.
I know the answer.
All right, but that's fine. Good job, Lloyd. Good job, Lloyd. Yeah, I know you know the answer, but yeah, it's 16. So therefore, x squared is 16. And when we take the square root of that, we get 4, which is why the absolute value is always equal to the square root of x squared and not x. If there are no questions, we're gonna move on to the next example. Does that make sense to you?
Yeah.
Okay, okay. All right, so David, you want to talk about this one? You're muted.
Sorry. So start with 1 plus 1 equals to 2. That's right, right? And then we subtract 1 from both sides. So 1 plus 1 minus 1 equals to 2 minus 1. And then we keep the left-hand side the same. But then on the right-hand side, we square the original number and then add a root outside of it. So if we square, so a square and a root should cancel each other, and the results should be the same. And then the left hand side is still the same, but on the right hand side, we times out this thing. So we basically distribute the factors, and it's if you remember the function, it's a squared plus, when it's a minus b squared, the equation equals to a squared minus 2ab plus b squared. So we get a squared is 4 minus so in this case, a equals to 2 and b equals to 1. So in this case, we get a squared, which is 4, and then minus 2ab, which is 2 times 1 times 2, which is 4, and then we plus b squared, which is 1 squared. And that's right. We move on to the next step. And we still have the left-hand side for the same thing. But this time on the right-hand side, because 4 minus 4 equals to 0, we could also write the equation into 0 minus 0 plus 1. That's right. Because 4 minus 4 equals to 0. And if we write 0 in a complicated way, 0 equals to 0 minus 0. So we basically we did a small trick from here to here. And we got 0 minus 0 plus 1. Now, if you remember the a minus b squared formula, this thing should seem pretty similar to you. Because you could see that a equals to 0 and b equals to 1. Why is that? Well, if you look at the equation, if we let a equals to 0 and b equals to 1, the result equals to a squared minus 2ab plus b squared. A squared will be 0 times 0, which is 0. 2ab will be 2 times 1 times 0, which still gives us 0. And then b squared will be 1. So this is a little trick we did here. We move on to the next one. We simplify this thing. We because we already know that this combination of number here equals to a squared minus 2ab plus b squared, we could simplify it into this formula, which is a minus b squared. We do the same thing here, and we get 0 minus 1 squared. Can you guys see why this happened? Do you guys have any questions? No? Okay, move on. And then
So what went wrong, right?
oh
yeah,
yeah,
you still gotta finish it real quick. Yeah, go ahead.
so the square and the roots cancel out, and you get 0 minus 1. And 1 plus 1 minus 1 equals to 1 plus 1. 0 minus 1. I mean, actually, you add 1 to both sides. And if you add 1 to both sides, the negative 1 cancels out. And you get 1 plus 1 equals 0, which means 2 equals to 0. Now, this is obviously incorrect. Can you guys tell me what went wrong?
What went wrong? That gave us 1 plus 1 equals 0. It actually invokes the same concept we talked about in number 3. Something involving square roots. Lloyd,
Good job.
excellent observation. Wait. Let Lloyd elaborate. Okay, Lloyd, what do you mean by this line? What went wrong here? What specifically went wrong? You can feel free to type in the chat if you want, or you can just unmute. Lloyd, if you're typing the chat, maybe like give us a thumbs up to let us know you're typing, because I'm not sure if you're like stuck or All right, he's typing. All right. Meanwhile, does anyone else want to take a guess? I mean, Lloyd already knows the answer, but it's good to come up with the answer on your own. Joyce, take a guess. You're smart.
Uh,
Lloyd pointed you in the wrong direction. I mean, in the right direction. Something with this.
what? I don't know.
Well, Joyce, don't give up yet. remember how we said the square root of x squared is the absolute value of x?
Yes.
Something to do with this. What went wrong? Here, Joyce, here's a little hint. What is 0 minus 1? Like, what does that evaluate to?
1.
0 minus 1?
0 minus 1. Oh.
It's
Negative.
-1, right? Right, Joyce?
Yes.
Right. So the thing I boxed up is equal to -1 squared, the square root of that. And then when we took the square root here, somehow we got -1 because 0 minus 1 is -1, right, Joyce? But look at this formula. So if you take the square root of -1 squared, what number should you get? Lloyd, that is correct. You should get 1. So instead of getting 0 minus 1, what you really should get is 1 minus 0, because you should have gotten the square root should have evaluated to 1 instead of -1. Do you want to say something? Go ahead.
I want to ask, why the 0 minus 1, why is there a little 2 on top next to the 1?
Oh, that's something called the square. It's like it's taking the number to its square. For example, if you write a little 4 and you write a little 2 on top, what that really means is 4 times 4, right? So that's 4 times 4 is again 16. You already told me that earlier. So that's 4 squared. It's something called the square. So when you write a little 2, it means square. Here, yeah, what's 3 squared?
3 is 9.
Excellent. You have mastered the concept of squares. All right, David, do you have anything to add on about this? No, not you, David.
Nope.
All right, all right. Does anyone have any questions about this? Does the square root thing make sense? No? All right, then. We shall move on to the next one. All right, this one seems a little scary, doesn't it? However, it uses the concepts we have already talked about. So I'm going to go over the manipulations real quick, and hopefully you can point us to the reason why it went wrong. So we begin by setting x equal to pi plus 3 over 2. Now, what is pi? That actually doesn't quite matter in this case. However, as a part of mathematical interest, I'm going to let you know that pi is the constant we use in circles, and it's an irrational number, meaning its decimals never end. And the first couple of digits are 3.1415, and then these are remaining digits. The list goes on forever, and it never repeats. So the digits are all random. If you want to learn more about it, you can do a little Google search yourself later and search pi. It's spelled like this. It's like an apple pie without the E. But anyways, we start by defining x equals to pi plus 3 over 2. And if we multiply both sides by 2, the equation remains the same, because again, remember, if you do the same thing to both sides of an equation, the equation remains true. Actually, another way you can think of equations is to think of it as like a scale. Like there's two things on, so there's things on one hand of line and things on another. And if you do the same thing to both sides, for example, add a pencil to both sides, to both hands of mine, the weight remains the same. And the equation is like the same thing. If you do the same thing to both sides, the equation remain a true statement. So multiplying by 2 on both sides, we get 2x equals pi plus 3. And then for the next step, we multiply both sides by pi minus 3 times pi minus 3. On the left side, we use the distributive property, and 2x times 5 becomes 2 pi x. 2x times -3 becomes minus 6x. The right hand side becomes pi squared minus 9. Someone tell me what factorization we used here. When? You want to tell us which factorization we used here? It's actually, we used it in the very beginning of class.
Is it a square minus b square?
Good. Equals.
Equals that.
And you want to express it in terms of a and b?
Basically a plus b in parentheses times a minus b in also parentheses.
Excellent, excellent. Right, that is exactly correct. And the name for it is the difference of squares. And so we use the difference of squares factorization, and we get pi squared minus 9. Then we add 9 to both sides. And we also add, okay, so this seems a little confusing, but because like from this line to this line, you can see that the 9 goes to the left-hand side and the 2 pi x goes to the right-hand side. So one way to think of it is that we added 9 to both sides. And this will get rid of the 9 on the right-hand side and put it here on the left-hand side. And we minus 2 pi x from both sides, right? So this would get rid of the 2 pi x on the left-hand side and put it here. It's a little confusing, but you can also think of it as like a positive on the left-hand side becomes a negative on the right-hand side. Does this line make sense the way I explained it? Do you have a question?
I have a question. What is the 2 something minus 3 equal to something plus 3 something minus 3?
Okay, so how do I say this? Well, first of all, this something here is a variable. It's called x. It's like the same letter except it's not y, right? It's like y is a letter in your name. This is x. It's the number it's the letter before y in the alphabet, and we're just using it as like a substitute, right? Like we're saying that x is equal to this number here, right? It's like a different name for the thing. This number here, this little squiggly symbol right here, is the Greek letter for pi, right? And as I have said, pi is an irrational constant, and it is equal to 3.1415926, blah, 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 blah. So that's just a number. You can just think of it as something like 3.1, or like you can even just think of it as 3. It doesn't really matter in this case. And here we're just multiplying them together. Does that make sense?
Yeah, maybe, but anyway.
Okay, you'll get it. You'll get it. Okay, continuing here. This line here. To go from this line to this line, we add x squared to both sides. And then using the factorization in which we have used many, many times in this one meeting, a minus b squared equals a squared minus 2ab plus b squared. Oh, this is not really working. Plus b squared. These two expressions become these two expressions. Hopefully, we've already gone over the formula enough times for you to understand how this works. But if it doesn't, please ask a question. Yeah, I'm gonna finish this and I'll get to your question real quick. All right. So taking the square root of both sides, we get 3 minus x is equal to pi minus x. And so canceling the minus x on both sides, we get pi equals 3. And this result is not correct because pi, as we have already said, is an irrational number. Its decimals never end. It is equal to 3.14159265358 blah blah blah. It does not simply equal 3. What went wrong? Does someone want to tell us? Joyce, do you want to tell us what went wrong? Do you want to tell us what went wrong? Somebody tell us how we got this amazingly inaccurate result. Are we a little stumped? It's something with this. Okay, so it seems that we are not quite sure what went wrong. Well, again, the thing that went wrong is the square roots. It's always the square roots. You go ahead.
Never mind.
Okay. Well, so what went wrong with the square root is that the right-hand side is actually correct, right? Because if you think about this, x is equal to pi plus 3 over 2. And if you subtract, okay, so how you can think of it is pi plus 3 is something like 6.1415 something, right? Because pi is 3.1415, so plus 3 is 6.1415 something something something. And when you divide this number by 2, you would get something like 3.07, like 7 something something something, right? It's like 3.07-ish. And it is definitely less than pi because pi itself is 3.14, right? So you can like compare these decimals and you see that x is less than pi. So if x is less than pi, that means pi minus x is a positive number, right? Does that make sense to everyone? Are we all on the same page? All right, so hopefully that makes sense. And then on the left-hand side, as we have already shown, x is equal to 3.07 something. So that's definitely larger than 3, right? And then if you subtract 3.07 from 3, that means you get a negative number, right? So when you take the square root of a positive number, it is equal to that number. But when you take the square root of a negative number, you get the opposite of that number. You should have gotten negative 3 minus x, because again, when you take the square root of x squared, you get the principal root, meaning you always get the positive number, which squares to x squared. Therefore, when you take the square root of this, it's actually negative 3 minus x, because 3 minus x itself is negative, and the number has to be positive. Therefore, we can now see that if you make this change, you would instead get x minus 3 equals pi minus x. And if you solve for x, you get x equals 3 plus pi, and thus x equals pi over 3 over 2, which brings us back to the original statement. And although that is a little redundant, it is indeed a true statement, which is what we should have gotten starting from a true statement. Okay, so does that make sense? Yeah, you said you have a question?
Yeah. What does the pi minus x mean?
What does pi minus x mean?
Yeah.
That's like saying, what does 4 minus 3 mean? It's like saying, when I have 4 cookies and you take away 3 cookies, you have 1 cookie left, right? Well, pi minus x is like the same idea, except it's just 2 different numbers. It's like pi, I have pi cookies, and you take away x of them. It's really just another way of writing this subtraction of 2 numbers.
I mean, like, how do you know that pi minus x equal to 4 minus 3 equal to 1?
It's not equal. It is not equal. No. That was just an example, right? So 4 minus 3 is a way of subtraction. It's an operation. Pi minus x is really just like you're taking x away from pi. Hopefully that makes sense. Okay, we're a little short on time here, so we're gonna skip these because these use the same idea. But like, feel free to look at them real quick, right? So like we start with negative 20, negative 20. We do a bunch of operations. We arrive at this thing here. And we take the square root. Of course, it doesn't make sense because this should have been negative. And we get 0 equals 1. These all use the same idea of taking square roots, resulting in false conclusions. But I'll post these on our website, and if you want to keep looking at them, you can later. But right now, I want to show you guys something that's a little different. All right, David, you want to do this one?
For this question, or not for this question, but for this example, we're gonna prove 1 equals to 0. So right here we have 0, and of course 0 plus 0 also equals to 0, right? So theoretically, we could add infinitely amount of zeros together, and we still have a 0 in the end. We're just repeating this operation here. So since 0 equals to 1 minus 1, we can all agree on that, right? 0 equals to 1 minus 1 because 1 minus 1 equals to 0. We can write 0 into 1 minus 1 plus 1 minus 1 plus 1 minus 1, because essentially you're just replacing 0, the equation here. 0 equals to infinitely zeros added up with this thing. Oh, yeah, you can't see it very well. Is it because it's too blurry, or is it because my writing covers some of the letters?
How about this, David? You keep going. I'll type the thing in the chat. Hopefully that makes it a little easier to read.
All right. So,
It's too blurry.
oh, okay.
Hey, yeah, I'm gonna type the thing in the chat. Hopefully you can see it better. Just go to the chat.
So if we rewrite this thing, we take the 1 from the first thing, from the first pair, and we take that out. We have 0 equals to 1 plus -1 plus 1, and then plus -1 plus 1. Essentially, we're just repeating this thing because we're basically grouping it like this, right? We're grouping the -1s with +1s, and we get this equation here. And keep in mind that -1 plus 1 equals to 0. So if we do simple calculations for these pairs here, we get 0 equals to 1 plus 0 plus 0 plus 0 infinitely many times. And we get that 0 equals to 1. This is obviously incorrect. Can you guys tell me why? When? Can you see the problem with this example?
Royce, take a guess. You're smart.
What about Joyce? No? All right. So if you look at this thing, the logic behind this example is actually quite simple. You take out a 1 here, and you pair up these numbers. You're eventually gonna, even if you repeat this calculation for infinitely many times, even if you rearrange numbers for infinitely many times, in the end, you're still going to be left with a -1, because you're essentially taking apart these numbers and putting them together again. So if you take out let's say instead of adding these stuff infinitely many times, we have 0 equals to 1 minus 1 plus 1 minus 1 plus 1 minus 1. This still equals to 0, right? If we do the operation above, operation the example did, we will get 0 equals to 1 plus -1 plus 1 plus -1 plus 1. And then -1, because we can't pair this -1 with any number. The reason of this is because we don't have any pairs after this. So we're gonna be left with a -1 no matter how many times you do this operation. Therefore, the 1 and the -1 should add up and give you a 0. And that is the problem with this question. Do you guys all understand this?
So basically what David is saying is that if you write the 0 plus 0 plus 0 as pairs of 1 minus 1, if you take out the pair and you leave the 1 out, you're always gonna have a -1 that's left using the logic of replacing zeros with 1 minus 1. So therefore, there should be a -1 at the tail end of this thing, meaning it should be 0. Does that make sense? Okay, that should be a good sign. All right, and also just to add on a little bit, this proof is actually in nature kind of illegal in calculus terms. It's something you're gonna learn when you're in like 11th or 12th grade, but the idea is that no matter how you distribute it, you're fundamentally writing it as 1 minus 1 plus 1 minus 1 plus 1 minus 1. It doesn't matter how you put the parentheses, right? Like you can put it here, you can put it here. It doesn't matter because when you add parentheses, it's still addition. It's the same, right? But if you do this, it is actually indeterminate because the result shifts. It always shifts between 1 and 0. So you actually can't determine if this string of numbers is really equal to 0 or 1. It is indeterminate because there is no limit as this approaches infinity. Therefore, this proof by itself is pretty illegal, but I guess it is pretty cool. It fools a lot of people. All right, so for the last thing, we got to show you this little little funny proof here. So we're gonna prove that a dog has 9 legs. So think about it. No dog has 5 legs, right? There does not exist a dog that has 5 legs. And if you don't have a dog, giving you a dog gives you 4 more legs than having no dog, right? Like a dog has 4 more legs than a dog that doesn't exist. Therefore, a dog has 9 legs, right? Because no dog has 5 legs, and the dog has 4 more legs than no dog. So a dog has 4 plus 5 legs, which is 9 legs. So a dog has 9 legs. All right. Hopefully there's no questions about this one. All right, we're out of time, so we're gonna stop here. But thank you very much for coming, everyone. Hopefully that was pretty fun. You can show your friends these proofs and confuse them. Just don't tell them what's wrong with it, or else they're gonna question you and nothing's gonna work after that. But yeah, thank you for coming, everyone. If there's any questions, feel free to ask. If not, bye. Bye, Loy. Good job.
Bye.
Bye, Joyce. Good job. Did you find these interesting? All right, all right. All right, good job, everyone. Bye. We're gonna end the meeting here. So